Our brains are hardwired to spot structural patterns. We look at the branching airways of a human lung and see the exact same geometry in a river delta, or we look at a neural network and see the structure of a galaxy. But visual similarity is not a physical mechanism. Assuming that a biological network operates the same way as a mathematical equation simply because they look alike is an epistemological trap. This animation demonstrates how a boundary can possess fractal properties while its internal volume remains entirely non-fractal. The perimeter of a Koch snowflake stretches to infinity, but it bounds a finite ordinary area. We have to separate the border from the bulk. In 1967, Mandelbrot formalized this problem of scale by asking a deceptively simple question: how long is the coast of Britain? The answer depends entirely on the ruler you use. A 100-kilometer ruler misses the bays and inlets. A 1-meter ruler captures every cove and jagged rock. As the scale of measurement shrinks, the measured length of the coastline actively increases. Relying on visual resemblance across scales without defining the ruler creates an optical illusion. It breaks the inferential chain between a mathematical observation and physical reality. To navigate complex systems accurately, researchers Jean-Sebastien and Hector Fernando Aguilar proposed a strict epistemological framework. Every scientific claim must answer specific questions. Name the object, the scale, the observable, and the inferential chain. First, you must specify the precise physical carrier or mathematical support under study. You cannot blur the line between a biological cell and a mathematical function. Second, you must define the exact spatial and temporal scale of the system before applying any analytical operator or measurement tool. Vague global concepts like consciousness or anesthetic potency cannot be measured directly. They must be decomposed into exact localized observables. Moving from quantum biology to macroscopic neuroscience requires maintaining this strict, unbroken chain of proof at every localized step. We can test this protocol first in pure mathematics, specifically by looking at the Fourier uncertainty principle. This diagram of a two-dimensional wave packet illustrates the classical Fourier limit. A wave cannot be highly concentrated in both position and frequency at the same time. A narrow position peak mathematically requires a wide frequency spread. For years, mathematicians attempted to apply this Fourier uncertainty to fractal sets by relying solely on the concept of fractal dimension. Dimension alone failed. Two sets could share the exact same dimension but exhibit entirely different wave dispersion behaviors. Proving uncertainty required a new structural constraint: line porosity. This maps line porosity, how a fractal set systematically avoids straight lines in space. It's a specific geometric construction, not general roughness. Alex Cohen applied this to prove the fractal uncertainty principle in higher dimensional spaces. These open linear pathways force waves to disperse. In pure mathematics, dimension alone fails as a metric. Researchers must isolate the specific geometric obstruction that forces wave dispersion to prove their claim. When we move down to the cellular scale, we face the same challenge: breaking down unobservable global states into measurable physical actions. In pharmacology, the Meyer-Overton rule historically linked an anesthetic's clinical potency to its solubility in a lipid-like nonpolar medium. But Meyer-Overton is strictly a correlation. It observes a relationship without providing a localized physical mechanism for how the gas actually blocks consciousness. To find that mechanism, researchers led by Travis Craddock shifted the empirical observable away from general neural membranes and looked directly at tubulin, the protein subunits that form structural microtubules inside neurons. This model maps a specific operator, quantum chemistry calculations of collective dipole interactions. It highlights oscillations occurring at a precise frequency band of 613 terahertz. Experimental data showed that when anesthetic molecules bind to tubulin, they specifically dampen this frequency band. When researchers applied non-anesthetic molecules to the exact same protein structure, this specific terahertz oscillation remained largely undisturbed. This measurement does not solve the entire biological mystery of consciousness. It rigorously links chemical polarizability to a localized terahertz shift, keeping the inferential chain intact. This demand for rigorous decomposition applies at the macro scale as well, specifically in clinical neurophysiology when trying to measure consciousness in vegetative or non-communicative patients. doctors cannot rely on subjective behavioral responses if a patient cannot move. Instead, researchers decomposed the state of consciousness into two measurable vectors: cortical integration and spatial temporal differentiation. To track this, Marcello Massimini, Adenauer Casali, and their team defined a specific empirical operator, the Perturbational Complexity Index, or PCI. This topographical map tracks the first step of the PCI protocol, applying a transcranial magnetic stimulation pulse to the cortex. This single magnetic strike successfully measures the integration vector by forcing disparate regions of the brain to echo back in response. Second, they record the resulting spatiotemporal pattern using an EEG, and they analyze the algorithmic complexity of that electrocortical response. By mathematically compressing this EEG data, much like compressing a computer file into a zip archive, they quantify the differentiation, or the pure information richness of the brain's reaction. The empirical observable is no longer behavioral wakefulness. It is the exact algorithmic compressibility of a magnetically induced cortical echo. When we evaluate pure mathematics, quantum biology, and clinical neurophysiology side by side, we find a common methodological requirement for scientific breakthroughs. The researchers involved actively refuse to claim that the brain is a literal higher-dimensional fractal, or that tubulin vibrations represent the entirety of human consciousness. Instead, they adhere to a core principle: unmeasurable global properties most admit rigorous operator-defined decompositions. In particle physics, the proton spin problem operates on this exact same logic. The global spin of a proton is an exact known value, but it requires breaking down into the angular momentum and spin contributions of its individual quarks and gluons using specific quantum operators. True interdisciplinary research does not blur the lines between physics and biology. It enforces the strict decomposition of unmeasurable global states. To analyze a complex system, you must define the exact limits of any projection or diagnostic tool used in your experiment. You must validate the precise physical and temporal scale at which the observable data actually operates, and you must know exactly what mathematical or empirical operator is generating your specific dataset. Relying on topological resemblance is easy. Tracing actual physical causality through layers of structural complexity is demanding labor. The future of complex systems analysis does not rely on finding universal visual analogies. It relies on ruthlessly maintaining the inferential chain,